Thanks for inviting me. So, spite of the fact that I never recently did anything with fermions, let alone doped fermions or anything like that. So it's a progress report on in terms of what we have been doing. So from our recent work, I thought what could be interesting to you guys is I feel if I show the computational power that we have or we don't have, that could be interesting for you to know what is feasible with superconducting qubits. So this is a picture of the team before COVID. This is the size of the current team. Actually, it's maybe 3 times this current size of this picture. But we wrote a work that has the word quantum in it, and it gets more than 100 citations per month. So I thought maybe you should know what is this about. Well, we made a chip, and with that chip, we posed a question that, of course, we know we could solve ourselves. And that's the story of the first part of the talk. But first, I want to tell you a little bit about the hardware of what it is. So it's all based on Josephson junctions. The elements that we play in is a 2-layer of aluminum, very simple superconductor, supposedly, separated by a thin layer of oxide. And if in 1960s or early 70s, they figured out that if there is a Ginsburg-Landau phase difference across are different, then the difference of the phase, this coherent phase, would lead to a constant current, essentially. And the change in that phase would lead to a voltage. So this is the building block, and it's very important for us because it allows us to make nonlinear oscillators. These nonlinear oscillators are like giant atoms. The level of spacing in these resonators is nonlinear, so we can address them individually. This distance, energy distance between 1 and 0 is different from 2 to 1 and so on and so forth. So you can really address them what you like. This is in contrast to the LC resonator that you could make by just piece of aluminum. And it's beautiful because it's big, in fact. Whoever told you it's disadvantage, it's not correct. Because this object that you see is 9 qubits, this is the capacitor, and there is a Josephson junction in here, hard to see. This is about 1 centimeter across, and you can bring wires to it. So you can control the individual qubits, and then there's a term between there's an element between them, which is a coupler. So what we're seeing here is a pattern of aluminum on. You good?
I didn't share the screen.
What you're seeing here is a pattern of aluminum on silicon, and the rest is painted in Photoshop. So you know the functionality of each element. So there's a capacitor, and there's a junction, and there's a coupler, and there are wires coming all around it. So every time you go to the board and write the sum of the terms of the Hamiltonian, for us, it translates every term in the Hamiltonian translate into a wire. And to wire a qubit, it takes about $1,000 just to get for the filters and everything to come down. But this is how close I get to Hubbard model. This is if you excite the qubits and let the photon and microwave excitations to interact with each other. At the end of the day, you have this Hamiltonian, which is both Hubbard Hamiltonian. So we could use this to study some dynamic of interacting bosons. But usually we don't do that. There are cases we can do it, but the whole field developed in terms of gates, and fidelity of the gates is really the common language we talk. So, but yeah, you feel free to think about it as a tunable Bose-Hubbard model. So the story of the first experiment goes like this. If you want to make build a quantum computer, and yes.
So if I do think about it in a Bose-Hubbard way, is there a max particle number precise?
No, but it's very hard to control or read out. These Bose-Hubbard ladders go as much as you like, but the fidelity of them is very low. You lose them very quickly, and you cannot read them.
I would also expect like these higher order terms become more relevant.
We can know them very precisely, but we cannot use them. So distincting 5 on one side versus 5, more than 3 on a given side is just hard to read out. But yeah, but the picture in the capacitance is telling you that if you know inductance and capacitance, you know the Hamiltonian really well. So if you want to spend billions of dollars and make a quantum computer, maybe the first question you should answer is there anything I can do with them that cannot be done with a classical computer? Let's just contrive a problem, define a problem ourselves, and see if we can solve even that before, ask government for millions of dollars. Because, when you go to the lab, these qubits are faulty and fall apart every second. You try to deal with them and try to make anything out of them. So the word quantum supremacy was coined by John Preskill about a decade ago, and it's an experiment that we define ourselves to beat a classical computer. So here's the sequence of the gates. You have a 2D grid of qubits. You make a 6x9, one of the qubits didn't cooperate, so you have 53 qubits. And you have a layer of unitary gates, a single qubit gate, followed by an entangling gate, and then you repeat this pattern for several cycles. So you start with the product state, and this product state, according to this unitary evolution, goes into a highly entangled wave function, and you're sampling bit strings from that wave function. And the claim is that we can produce bit strings that, according to Born rule, coming from that wave function, with higher fidelity than a classical computer can do. That's the claim. And it rests in two things. I go quickly over them. One is that you have to be sure you kill all the symmetries in the problem. So all the Hilbert space that is there, you're really using it. So it's the notion of complexity. I'm using a maybe familiar example. If part of the Hilbert space is not used, meaning that there are sorts of symmetries in the system, and the problem is not as complicated as you might think about. So you have to really be sure that the dynamic is really ergodic. But making an ergodic dynamic is not very hard. You just put random numbers in the Hamiltonian or the unitary. So everyone who made a mess in the lab knows it's not just hard to make something complex. But the challenge is to be on top of the fidelity. You have to speak in the language of fidelity. You have to produce that complex dynamic under your control on demand. You can speak about, you have to put a fidelity tag on it. And that's the challenging part. So for the first part, complexity part, I quickly mentioned that this is a kind of our indication that let me just say this, that you can choose a subset of qubits, 3 by 2, 3 by 3, or some small number of qubits, and you can run a sequence of the gates on them, the ones that I showed, the random quantum circuit, and you can sample the bit strings. This is what you can do for a small system. You can say which bit string did I get with how many times it repeats itself. And these are, and then if you, so this is the number of the times that the bit strings appeared after a given unitary dynamic. And you can sort them, just take the tall ones, put them to the left, short ones, put them to the right. Now forget about the index and just sort them out. And there's a way, the function described that is I forgot, this is the exponential, or this is the logarithmic one. So whatever the way you look at it is the exponential or logarithm. It's a Porter-Thomas distribution. And if you obey that, then there's a good evidence, not probably full bulletproof proof for it, that there was indeed the dynamic was ergodic and the entire Hilbert space was used. Okay, so there's some math goes into it. So but you cannot do that for the full experiment, which has 53 qubits. When you get to the 53 qubits, you have a Hilbert space that is 10 million billion dimensional. So you cannot really get probability. You're not going to see a bit string twice. But for a small subsystem, you can convince yourself that dynamic of ergodic.
Question, just to make sure I understand which dynamics. Should I think about the dynamics with that both the upper field?
Oh, sorry.
More like some gates which you apply.
These gates. Single qubit gates, I should have said that. Single qubit gates put you an equator. They are either the square root of x, the square root of y, or square root of w means 45 degrees between. The entangling gate is almost swap gates or I-swap gates, but there is some phase. I show you the 2 qubit unitaries later. So the name of the game is that I show you this gate sequence and we say, who can predict the outcome of this sequence? So
why not just let your system evolve with the
because notion of fidelity, because of very you could do that. It's as strange as it is. when you try to turn on this Hamiltonian, the qubits are some idle frequency. When you bring them together, there's few nanoseconds. It's very hard to know what is your Hamiltonian. And that is sufficient to discourage the entire community from doing it. And also, historically, people like to write gates, I guess, is very sad fact of life. Yes, you could do either way. Okay, so there was the notion of complexity, my evidence for complexity. Now I go to the evidence for fidelity. So here is a bit philosophical question. How would you do something that you can prove you cannot do? Right? You want to show that you are incapable of doing something. Is it bit chicken and egg? How you would do that? Well, we got lucky. The lucky thing was that the sequence of the gates really matter. So meaning that this notion of fidelity, the complexity is very fragile. If you do A, B, C, D in the choice of the 2 qubit gates, and then you repeat it, the pattern after 4 times, then this actually is a very simple problem. If you repeat the gate A, B, C, D, and then you repeat it slightly differently, and then after 8 times you start repeating itself, this is not simplifying for the problem. So the physics is that how entanglement is spread across the chip. In this case, you can find shortcuts and you can simplify. So with the tiny changes in the gate sequence for experimentally shouldn't be inconsequential, I have something which I can very easily classically verify versus something that we cannot do. So how do we define the notion of fidelity? Essentially, we get a bit string I and say what was how many times that bit string appeared, and compare it with the probability that the computer tells you that that bit string should have appeared. So this is just the notion of entropy, and that tells you what was the likelihood of that gate. So the formula is slightly more complicated because you have to normalize it. You have to be sure when your bit strings are just randomly generated. You just have to go. The fidelity has to go to 0. But the essence of it is this Shannon entropy. But actually in the lab is a slightly complication and simplification in a sense that you get a bit string xi, it's not going to repeat itself in the 10 million billion dimensional Hilbert space, but with classical computers tells you the probability of it. So and this is just simplified version of this under the Porter-Thomas assumption. So that's what we use over the large Hilbert space, but the parent equations are obvious. So I just mentioned that the choices of the gates have, you can have choices, and it's extremely consequential in the complexity of the sequence. But first thing we would do, of course, is that you draw as if you have 2 separate chips. You do not connect any entangling gate between left and right. You have a chip of 26 qubits, you have a chip of 27 qubits, no entangling gate between them. And this is, of course, you can fit it in your laptop. And you can see the fidelity of them regardless of the sequence of the gate. These are really small problems. Then you might be a little more brave. So what you could do, you can let the left side and the right side don't talk with each other for a couple of cycles, and then only later on the evolution you let them talk to each other. So you turn on the gates slightly later on. And in that case, you can compute them here, and I think in here too. So this is more manageable. But of course, when you turn on everything, then there is no way that you can compute in here. What I would ask you to believe me is that the difference between these two is just changing the order of the gate. So the fidelity should be unaffected. If you don't believe that, well, then there's nothing I can do. Maybe I can bribe you, but that's all. So there's no way to put red points on that side because the sequence of the gate is such that the computation is very hard. But if I just reorder them and you don't think something goes crazy, then we can know that indeed we have done them with high fidelity. So what I'm asking you to believe that the red point would have appeared in here. So how long would that take? So you see sometimes for how long it takes to do the computation. But you may notice that I've been very unfair to classical computer. I asked what's the wave function coming out of classical computer. Why the fidelity of my quantum processor is really awful. The fidelity is 10 to the minus 3. 1 out of 1,000 bit string is correct, right? There's no right and wrong, it's probabilities, but most of the bit strings are wrong. So you can simplify it by that fidelity factor, and this famous 10,000 years that you heard whatever in the news is coming from here. When you simplify it, you allow it to be wrong as much as the quantum processor is wrong, it still our approximate estimate is that it takes 10,000 years. How do you do these computations? Is interesting maybe to highlight that. These computations don't take that much time if you could fit it in your memory. And I don't know what I'm saying, but I'm going to say you have to do it in RAM. You cannot do it in hard drive. They told me to say that. I don't know what exactly it means, but it means that maybe you remember this. The thing is that you see, you go the color is the time it takes. It's the number of qubits going deep. So if you could fit it, let's say 2-core laptop, if you put it 1 minute in your laptop, 30 minutes depth 10, other depths also fit on your laptop. So as soon as you fit the wave function in your RAM, you're good to go. But here is the thing: on the planet we live in, this is the amount of RAM available on this planet. So there is no supercomputer that we know on the planet we live in. New York may be on a different planet, that this is the amount of the RAM of the supercomputer available. So of course, if you could fit it, 50 qubits, depth 20 could take a day, but we don't know how to fit it in any memory, okay? So that's the subtlety of the argument. It's not, that's where the sentence, the RAM has to be in the RAM. Of course, I was telling about patching and breaking into two, so you can do trade-off between a space and time. You can do two things and then consider all the possible ways that the left and right could have talked to each other. You can do trade-off and losing time, but at the end of the day, we claim that we did the best trade-off for you and still you're gonna lose. And that's it. So one thing I want to highlight is that this is all about fidelity. If the quality of the gate were 10 times more or a few times more, I've shown you the fidelity of the gates, let's say the 2-qubit gate. If it was 3% error gate, our gate fidelity is somewhere between 2% and 1%, so it's somewhere in between. The problem would have been very much simplified. This is very important to keep in mind that we did all this careful analysis to figure, and this is how, since that's why supremacy was done in 2019 and not 2009. This is really key concept that we always take into account, and we are very hesitant to play numbers without having fidelity. So this is also a big piece of the thing. Okay, here's the good news and the bad news. We are not the world record holder anymore, both in terms of the computational time and both in terms of implementation and the hardware. Two distinct Chinese teams outperformed us. We are happy that we led to development of tensor network contraction business, and lots of ideas, advancement happened in there. So the computation that we claim it takes 10,000 years, it now takes about a few hours. So, because, well, at that time I was clever enough to put this to save our rear end, because we say that, hey, look, it's about the physics. It's going to keep going. You know, the numerical is going to catch up, and we're going to catch up, and it's going to go forever. But the physics, as we all understand, one is exponential, one is just polynomial in the number of the resources. So, anyways, yeah. So the record holders are two Chinese teams that they show how to do these things far better than us at the moment. And yeah, we haven't been quiet either, so you hear from us soon. Okay. So how much time I have? I want to get to the second experiment now.
We still have 10 minutes.
10, okay. Yeah. Maybe I heard wrong. So 10, 15. Okay. So this is interesting. Of course, you get as soon as you get all the visibilities with this experiment, they say, okay, well, let's do a contrived example. Can you do something interesting? Can you do something useful? And okay, we start thinking, what can we do that is interesting or useful? One thing, of course, you could do is you can make a few hundreds or thousands of qubits, and you don't need to make them much better. You know, it's slightly better than what we have. You make lots of them, and you make a fault-tolerant quantum computer, and you cure cancer and all that. Another way of thinking about it is that, well, okay, I don't want to make many more qubits, but what can I do? And these are the problems that we think is going to come to our horizon if we make our qubits orders of magnitude better, but not that much in number. And I'm going to give you an example, and I think you can see the common theme is the study of non-equilibrium quantum dynamics, quench dynamics, come to our horizon very, well, is the underlying, well, we talk about different physics there, but one of them that I'm picking up to talk today is this work, which actually will be in press a few weeks from now. Is done fully by Googlers this time without collaboration with external people. So here's the study. Here's the physics of it. You guys are familiar with XXZ Hamiltonian for the Heisenberg, and you know that this is solvable by beta ansatz. And there is a work by Esslin. Maybe I forgot that. I got that wrong. That they show that there's a bound state. So if you know it's integrable, then there's got to be a bound state in it. It's just a matter of someone who's willing to figure out the bound state, and then the team of Emmanuel Bloch actually experimentally observed the formation of the bound state in the Heisenberg model, or I don't know, maybe away from the in the anisotropic limit. So you can see it. And then there's a work by Thomas Rosen who says that the Floquet version of this Hamiltonian, now you're going to essentially a kicked version of it. You're going to kick to this term and then kick to this term. And this is the Epstein gates I explain in a second. He showed that this is also integrable. Then Igor Alainer wrote a very detailed article of 100-some pages, and he said that, well, it's also there's a bound state in there. And our task was to figure out and find this bound state. So this Epstein gate goes back to your question, is the gate that was also used in supremacy. In the supremacy experiment, this theta was close to pi/2, and this phi was maybe close to 0 or something. Here, I'm going to play with these numbers to take them to the limit that Igor tells me to anticipate seeing the bound state. So what's cool about it is that when you have a band of states forming in the presence of continuum, and yet is stable. You know, the excitations that you see in maybe semiconductor physics, they are in the middle of the gap. Here now you're going to see them that they are coexisting with the continuum of the states. I will find evidence for you for that. So what do I mean by bound states? What I mean that I'm going to get a chain of qubits in a ring of qubits. In fact, I'm going to excite a couple of qubits next to each other. And as I look at them later and later instance of time, I see these excitations are together. They cannot get divorced from each other. They are bound together. They are always together. That's what the first evidence I provide, and then I provide further evidence in terms of the backstructure. The hand-wavy argument from Feynman-Pack integral is that for the two photons not to be together, here are a couple of possible scenarios. They accumulate phase when they are into each other, next to each other, and then they don't accumulate phase anymore. And if you add over all these possible paths, you would see that there would be they add up the complex phase that they essentially cancel each other. So scenarios like this would possibly cancel each other if they start the scenario operate. Okay. So we're going to get 24 qubits. We're going to put them in a ring. And we are going to start with the initial state, which is a product state with a couple of photons excited next to each other. And we're just going to look at it as a function of time and space. Well, first I put 1, and there's nothing to be bound to. So I just have a very happy random walk in this ring. And then I say 2 and all the way to 5. And then you see that when we just measure bit strings over and over, you see that there is a concentration of color, essentially indicative that the photons don't want to get away from each other and they stay together. Okay, it's a very weak evidence for what I'm just saying. But what I could do is I can separate my bit strings that I'm recording to T1s that are together and S1 that are separated from each other. And if I have a T-bit string, then I show you only where the T-bit strings are, and I can show it with their center of mass, because T-bit strings, they are together, so I can use one pixel to show where they are. And you see, when you look at these two, for instance, it's very much similar to the pattern that you see here, only it's slower. Oh, I would not show you theory. Why should I do that? It's all experiment. I would not betray your time with, so, and also you can go look at the envelope, and the propagation is ballistic, meaning that there's not that much junk left over, so it's good at propagating very nicely. And you can extract the maximum velocity, that's just this slope in here. And it goes according to Igor's prediction. Okay, maybe that's too much. So and now I want to go tell you a little about how we get to momentum space picture. Be good? Yeah. 5 minutes, okay, that's perfect. So I want to take you to the momentum space picture. I want to show you band structure. You guys are condensed matter. You want to see that. We have a way to do that. It's not scalable, but the idea is that you can put a couple of qubits on the equator, and if you get clever in by measuring some correlation at the end, because this U is photon number conserving, you can really essentially do the green function for the system in a very unscalable way. So for instance, we go using this formula up to 5 excitation. You have to add 32 terms, and they are Pauli's of length 5, but it kind of more or less works in a very, very limited manner. So we did a single photon of it a few years ago. So here's what I'm suggesting we should do. We measure the expectation value of this raising operator is non-Hermitian, but you could do it is by just adding these Hermitian terms and just add them together. You do 4 different measurements and you just add them up. You get as a function of a space and time, it looks like nothing, but then if you add them with the complex 3-factor dimension and you fully transform it, you see something very nice band structure in here. This is for 2 photons. You see a band very much looking like the E versus K of the tight binding that you're familiar with. In this case, it's slightly more complicated. Is cosine of E of K is cosine of K. So it's a little more into it. But essentially it's the same. We can continue this brute force method, let's call it. We can go all the way to 5 photons. You can see that these bound states, these photons are forming a quasi-particle, and this is the dispersion relation of these molecule of photons, or this quasi-particle of the photons that are forming together. The band is getting more flat as it gets heavier. One thing that you can do with this gate is that you can have a single qubit rotation before and after it, which effectively act as a synthetic magnetic field penetrating this ring. And because it's a closed ring, it cannot be gauge transformed out. And we can play with flux, essentially going to penetrating this. And you can see the bands are moving right as you change the flux going down. And the rate that the bands are shifted allows you to essentially extract a pseudo charge of this quasi-particle, which is the bound state of the photon. And the matches, God forbid it doesn't match Igor's prediction, but it does it well. Okay, so this was all maybe a little known physics, but here is the glimpse of discovery, how it looks like. Our guru wants us to do something beyond what the integral model does. So what we did is we get a ring of 14 qubits, and it started to add an extra qubit, going quasi 2-dimensional. And by that, we would break the integrability. And when you do that, the naive thinking or the simplified thinking is that where the Fermi golden rule tells you that as soon as you start this perturbation is quantified by the strength of this theta prime coupling to the second dimension, this quasi 2-dimension. As soon as you put that, the Fermi golden rule probably suggests to you that the bound band would be gone. And probably by the tone of my voice, you've got that this is not actually what's happening. So this is the strength of the bound state, how robust it is. And in the absence of perturbation, that's the top line. As a function of cycle, because there's replacing the system, it goes down with a certain rate. So this is numerically would be a perfect flat line. As you put a very strong perturbation, theta prime, as strong as the one that is creating the dynamic, you would expect that it goes down here. The dashed line is just drawn by hand. But actually in the experiment, this is not what happens. So there is certain resilience to the bound state to this integrability breaking mechanism. Let me show you more data. You can go systematically change this perturbation, and you can see that this is going down very slowly. I can show you the same data slightly differently, that you can see as the order of the perturbation, we make a cut in here and here, it stays put together, and then it goes down. Is interesting because as soon as you introduce this extra dimension, you are offering a 3 times more Hilbert space dimension. Yet they refuse to use those parts of the Hilbert space. That's the beauty of it. We can do the same thing in momentum space. We can do the brute force Fourier transform. I told you tells you that bands. Of course, if you make the perturbation very strong, it breaks. But the rate of the breaking, the strength, the full width half max goes down very, very different than what a naive thinking would suggest. So we cannot explain it, and that's really good. But it's not that we didn't think about it. But it says that some thinking is needed in here. Okay, so. Is there any hidden conserved quantities? We don't think so. I'll show you how we break integrability in a second. This physics of pre-thermalization and whatnot, no one ever think about them to do this so far from such a strong perturbation. So if that's the answer, that there's some behavior like that is happening, it by itself is interesting because we're suggesting there's a new regime that this is still works. So it's not a priori obvious. And there could be emerging symmetries. Well, it's kind of topology because how can I project that? It's a weird thing to do. Well, here I'm showing the level of statistic coming later on, which shows that indeed we are breaking integrability as the way we are hoping to do. And here is, I think, my claim to discovery. This is a numerical work, of course, can be done in a laptop. It's not that complicated, and but what I'm saying is that it only came after we did our work. So in a sense, it was the first time that superconducting quantum processors were leading the discovery. Well, it's not maybe earth-shattering discovery, but it is what it is. And it inspired this numerical work and further investigation. Thank you.
Yeah, let me put you circles on your little circle, but you add your qubit on the few edges, and we hope to see some kind of movement of your
This geometry.
Yeah. So would you expect the same thing if you were to just instead of putting 7 qubits on the edge, just one new string of qubits giving out, and here you could actually have a leakage of your
Probably. Well, you see here now we are giving them 7 chances to escape, and they didn't take it. So if you do one long chain, I don't know. Probably
a little bit of, let's say, you just like open a door for like a closed closet, and therefore like there's.
Yeah, I don't know. Well, I think the thinking is you have to look at the level of space. Yeah, to see how much you really break the integrability by doing that. Yeah, I really don't.
So something that we were discussing when we did this experiment in Munich was basically colliding L-string.
Yeah, you never figure out how to give it this definite K.
I know, but it doesn't matter, right? I mean, start 2 here and the waveforms go together, and you can still deal with it.
Yeah, maybe. Yeah. You have some time.
Maybe something like
before they come from the out.
Yeah.
You have some time. Yeah. Yeah, that's
also for integrability testing, right? Because then you can kind of smash them against each other and maybe see how they are, and maybe just change.
Yeah.
So concerning the quantum supremacy itself, right? So as you know, it was shown that simulating this process with a fixed given error, right? With classical algorithms has the network just a few hours in the lab, right? So can you comment on the comparison about quantum supremacy between the Reynolds and the NISQ machine?
No, our numbers are NISQ machine.
I know, yeah,
So,
that's precisely the point. So the compression algorithms that quantum networks provide,
now it's from 10,000 years, now is 1 hour.
There are new algorithms that.
Yeah.
so do you know this paper by Meyer and Hassan?
Not that, no, but these guys really target what we claim and they outperform us. So we are beat them already. I'm missing something.
Well, I'm not familiar with those papers, what else?
Sorry, I don't have the reference, that's my fault.
Schubmeyer came after.
Oh, no, I do have the reference. Huh?
Schubmeyer gets that 15 hours on 512 meters down to like 30 minutes on a laptop.
Yeah.
But a few more qubits would make a big difference again.
No, that's not the point. That's not the point.
No, you cannot constantly outperform it. No, this is one is growing very differently.
It's probably a discussion for topic.
Sure.
And just to understand with this robustness of bound state.
Yes.
So the geometry is just like you show us that essentially every second site has a loss.
Yes,
And
yes. Well, the coherent.
And you know, the thing that now the bound states are now such that they are trying to avoid those losses. Like if you look at the real space picture, you can just see that they get larger.
I didn't do that.
But they can stay bound, but avoid loss to sight. And then it's something that no piece of control zero kind of effect. If you try to measure something, then a certain size becomes necessary.
Well, okay, so maybe what you're saying is that here, what I call a cycle is that the qubit talks to its left and then talks to its right, and I call it a cycle. And I never show you half cycle data. You might saying that it might go to those sides halfway and come back, or some destructive interference. Yeah, I didn't look into that. Yeah.
It's like intuition is such that imagine that I just like those sites instead of losses with a very high potential, right? So then obviously like your particles would try to avoid them. But they could still move together, sort of getting over this barrier.
No, but the coupling, right? So this is the way dynamics is in the chain, but the coupling to external is exactly that, right? This is the same gate that.
That's correct. But think of it, it's like time binding model, right? And now you make certain types to cover repulsive potential. That would still not kill your bound state. It would still go over this repulsive potential through some kind of virtual process. And I'm saying that actually strong losses in many cases act as a strong repulsive potential.
Yeah, I don't know, but
it would be interesting to look at real case that maybe what's happening is that now your bound state is very broad pattern, and they manage to avoid those losses, but they still.
wouldn't you see it in the momentum picture? Maybe I don't know.
Maybe I'll ask you what Denver question, like, was entanglement ever used for something? And could you find that because you had entanglement in the quantum circuit, it did something?
That's an underlying thinking.
Because right now you're just manipulating local beats, so.
No, but entanglement grows. I have other data that shows that a subset of qubits get maximally entangled with the rest. I can show you later. Yeah, there is.
So on your list of mechanisms for current instability, you didn't include scarring. I'm wondering if you thought about that as a potential mechanism, or have you tried in the initial stage to see if maybe.
No, but the initial state is set, right? They are together. So they are.
So I guess what I'm saying is that would all of this instability disappear by virtue of that initial state? So there's somehow special.
But that is part of the definition. If you're together, or they stay together. Yeah, okay, maybe I see what you're saying. I could perturb the wave function rather than the Hamiltonian unit.
I mean, the way.
Yeah, yeah.
Okay, I think we should move on.
One last,
One
organize.
last question for organizer.
What about stimulating Fermion?
No, Fermion. Okay, maybe I should address that. Yeah, no, the fermions have something called, Jordan-Wigner transformation and long phase, and it's very costly for us.
Do you think it's going to stay possible or otherwise?
So long as they meet Jordan-Wigner, yes. Yeah, I think so. I think so. It's very costly. We tried to do a spin charge separation. It was just many gates to show something that you guys showed trivially, we just couldn't do that. Yeah.
Okay, let's thank